Hello, hello again. Let's talk about weak bases this time. All right, now the beauty of weak bases is it's the flip side of the weak acid. So everything we've done is pretty much the same, only I'm now talking about the base side instead of the acid side. All right, so step number one, what in the world would be considered a base? Well, there are two types. We can have molecules and we can have anions. So what kind of molecules are we talking about? The one that we use most often, and the only one that we're really interested in this class is ammonia. Okay, so the molecular compound ammonia, when you react it with water, produces hydroxides. So what does a base mean? It means it produces hydroxide when you put it in water, either by dissolving or by reacting. All right, so let's take a look at how ammonia does that. So ammonia plus water, the ammonia will actually rip off one of the hydrogens of water, and it will donate its electron pair in to make ammonium and hydroxide. So remember, every time you see aqueous ammonia, that means ammonium hydroxide and vice versa because they're in equilibrium with each other. And it is a base because it produced hydroxide. Okay, beautiful. That's your molecule. Well, what about your ionics? All right, any ionic with hydroxide is considered a base because when you put them in water, it creates the hydroxide. And then last but not least, what about these anions? So let's just take F minus. All right, if you react with water and it produces hydroxide, you would be considered a base. So this F is going to rip off a hydrogen, donate that in, and it's going to make HF plus the hydroxide ion. So again, by definition, those are all bases. Wait a second. This is a weak acid. Yes, it's a weak acid, which means the proton is sticking tight to that fluorine. So overall, what it would do to water, though, the free ion would be hydroxides. Now, which anions aren't fair game? Those that come from the strongies. Okay, all right, gonna go over to the whiteboard. Well, maybe I'll just do it right here. No, I'm not. Listen to me arguing with myself. I do it all the time. Sometimes my best arguments are with myself. All right, weak bases. When they dissolve or react with water, it makes hydroxide ion. All right, so we have seen ammonia, and I'm going to write that water a little differently so that you can see it. That lone pair on ammonia rips that hydrogen off. It makes NH4 plus hydroxide. All right, this is a weak base, so the K value would have a subscript B. So Kas have protons in the product side. Kbs have hydroxides in the product side. And we can look that up in just a moment. All right, so there is your molecular. And then anything with, let me see, so calcium, let's just do zinc hydroxide. Any ionic that has a hydroxide. Remember, this isn't reacting with water, this is just dissolving, so this is a dissociation. That also has a K okay, value. But in this case, it's not a KB because we're starting out with solids. So this is a KSP, but it's still considered a weak base because it produced hydroxides. And then last but not least, the ions. And let me see, I did fluorine last time. Let's do, yeah, I can't believe I can't think of one. Come on, who do I want to use? All right, we'll just use sulfur. All right, sulfur will rip a hydrogen off and it will make HS minus plus hydroxide. So again, it still created a hydroxide. Now, what kind of a K value would this be? All right, it is producing a hydroxide, and this one is going to be a KB because it was not a solid being dissolved. And if you'll notice, this could react again to put another proton on. So that would be KB1 and KB2. Oh, okay. Let's go to the reference sheet and look those up. All right. Now, if you're looking at the reference sheet, I'm looking at the orange pages. On the left-hand side are all those acid ionization constants, okay? And in the top right, there's not very many Kb values, and the reason for that is if you have a Ka, you always have a Kb. So it's just like pH and pOH. If you have one, you always have the other. But let me see, ammonia is 1.8 times 10 to the minus fifth. Okay, KSPs will come in the next couple chapters. And, oh, I can't find this HS and this H2S, and that is because I didn't give it to you in base form, I gave it to you in acid form. So there's this very nifty property, and guess what? It came from water again. That the Ka times the Kb is equal to the Kw, because what does water have? Protons and hydroxides. And so the Kw value is made up of both the acid and basic properties. And so if you have one, you can always get to the other. All right, so let's figure out what this value is. So H2S, okay, this is what we would look for. This was what we would look for. Different color. I would look up the K value for that, and the K value for that one is hydrogen sulfide is 1.2 times 10 to the minus 13th. And Ka2, or let me see, that would be Ka2, and Ka1 would be 8.9 times 10 to the minus 8th. So if I want to find Kb1 and Kb2, notice the numbers are different. Okay, the numbers are different. So if I want KB1, I need KW divided by KA2. And if I want KB2, I need KW divided by KA1. And that is how you would figure them out. And calculator. Ta-da, 1 to the negative 14th divided by 1.2 to the 13th negative. And so 8.3 times 10 to the minus 2. And better check that again. 114, 1.2, -13. Okay, 8.3 -2, and KB2 is going to be 1 to the -14th divided by 8.9 to the 8th. And so 1.1 times 10 to the -7th. Check again. Yep. Okay. And that is how you would go back and forth in between the KAs and the KBs. So remember, if you know a KA, you always know a KB, and vice versa. If you know a KB, you can always find a KA. And that is why I give you so many KA values, but I don't have to give you that many KBs because you can convert them for yourself. All right. Can you write an equilibrium expression for these equations? Well, sure. A minus, K generic base right there, is, sometimes I put a B, by the way. The reason I used A minus is that came from an acid, okay, but a B minus works there just as well. So B plus water makes the hydroxide plus HB if I was using the letter B. All right, so KB has a hydroxide always as a product with the weak acid over, in this case, it happens to be an anion. And can we do this same thing? pKb's equals the negative log of the Kb. And so remember when we did that with acids, the larger the pKa, the weaker the acid. Okay, there's a little mantra for bases too, but I suggest you remember the acid variation, and then it's pretty much opposite for the bases. And then don't forget, if you know one, you will always know the other. So let's do our favorite one, acetate. Okay, what is the Kb for acetate? Well, you have to look and go, what would your acid be? Okay, put a hydrogen on there, and what would your acid be? And in this case, it would be HAC. And so if I look up the Ka of HAC, it's 1.8 times 10 to the -5th. So Kw is equal to Ka times Kb. So Kb is equal to Kw divided by Ka, and that should come up at 5.6 times 10 to the -10th, times 10 to the -10th. So when you are given the anion, look and see what it would be in the acidic form and look at that Ka, and then Kw divided by Ka will give you the Kb. Ah, weak bases. Love them, love them, love them. I'm trying to decide. You know what? I'm just going to do one of the problems on this video too. So I'm going to go down here. I also give you some weak base problems. All right. What is the hydroxide and the pOH for the dissociation of 0.2 molar sodium fluoride? And notice I'm giving you the Kb, but you would be able to get that off of your reference sheet. And can successive approximations be used? I cannot stress enough, this is the exact same setup. It's just a base instead of an acid. Step number 1 has not changed. I need a balanced chemical equation. All right, what about this sodium thing? Completely ignore the sodium. All sodiums are 100% soluble. So really what I'm asking you to look at is this, is the fluoride. Well, what will an anion do in the presence of water? It will react with it to create HF and hydroxide. Can you write out an equilibrium expression? Yes. It made hydroxide, so this is a Kb, HF, hydroxide. Water does not appear, so on the bottom is just F minus. All right, can we find that? Why, yes, we can. 1.4 times 10 to the -11th. Okay, what do we know about the initial concentrations? Well, it looks like we had 0.2 molar fluoride. I didn't add anything to it, so these are 0. So minus x, 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 and this is 0.2 minus x, x, and x, because none of them were given. Oh, okay. Well, guess what? I have a KB, but all of my equilibrium concentrations have x's in them. So I'm going to plug it in. So 1.4 times 10 to the minus 11th is equal to x squared over 0.2 minus x. Again, I'm going to make the assumption that this is a weak base, so I'm going to ignore that. So x is going to turn out to be 1.4 to the negative 11th times 0.2 and square root it. So 1.7 times 10 to the minus 6th. I'm going to confirm. And 1.7 times 10 to the minus 6th. All right, what is x? X, in this case, happens to be the HF and the OH. So 1.7 times 10 to the minus 6th molar, 1.7 times 10 to the minus 6th molar. And shouldn't I, check that and make sure it was valid? Yes. So let's just do a quick check. Divide it by the original, multiply it by 100, and whoa, 8.4 times 10 to the minus 4th percent. Yes, it is less than or equal to 5%, so okay. Although it is getting closer to that water number, but we're still okay for that as well. So yes, I can use that approximation and I can ignore water still. So those are my concentrations. And then 0.2 minus 0. Wow, 1, 2, 3, 4, 5, 6, 7. It doesn't change that value at all. It was a very good approximation. All right, there are my equilibrium concentrations of all the species, but I also wanted to know what the pOH was. So the pOH is the negative log of the hydroxide, which is 1.7 times 10 to the minus 6th. And my pOH is 5.78. Did we expect? Oh, be careful. Yes, I know that number is 5.78, but it's a pOH, not a pH. So if that bothers you, add 14 to it, and the pH is 8.22. Did we expect a basic pH? Okay, and the answer is yes. Now, there's nothing wrong with leaving it as the pOH, but don't forget the pOHs are just kind of backwards. So 5.78 in a pH world would be acidic, but a 5.78 in a pOH world is actually basic. All right, there's your intro to weak bases, and until next time, Jolly out.